All right, so next up, we're going to take a look at the electron configurations of transition metals. So let's draw our diagram of a periodic table again. And remember, we call this the S block over here. This is the P block, with helium being part of the S block, just kind of weird. And then over here, we have the D block. And the D block are our transition metals. And remember that these transition metals are N-1, N-1. So let's take a look at what that looks like. So we've got our periodic table. Let's take a look at the first transition metal right here, scandium. So again, we can use our noble gas to say that scandium has the same electron configuration as argon and then some. We're at 4 here, and remember this is the S block. Both of these are filled. 4s2, right? And now we get to this one right here. We're in the D block, so we put D. And remember, this is N-1. So instead of being 4, this is 3. So 4s2, 3D. And then we have this, how many electrons in this D orbital? Just 1 in this case. So there's that for that. And then the question might come up of valence electrons. How many valence electrons are there? And depending on who you're asked, you're going to get different answers. And so this idea of valence electrons gets a lot more complicated for transition metals. So valence electrons idea more complicated. And so we're just going to ignore it. I'm not going to ask you how many transition metal or how many valence electrons a transition metal has because it's actually quite a complex question. And so the transition metals go on like that for quite a bit. Let's take a look at chromium next. Chromium. So again, chromium, we can say, looks like argon, and then 4s2. And then what you would think it would say 1, 2, 3, 4. What you think it'd be would be 3d4. That's what you would think, right? Or maybe you might not think that. I don't know. But in reality, it's actually different. If experimentally it's been shown that argon has a electron configuration of 4s1, 3d5. So one of the 4s electrons goes ahead and jumps into the 3d orbital. And so this one up ahead is wrong, and the one below is correct. And the same thing happens for molybdenum. Molybdenum is right under chromium. So you might think it's 5s2, 3d4, but it's not. It's 5s1, 3d5. So that's weird. Some exceptions there. Some other transition metals are pretty normal. And then we get over here. Copper, silver, and gold. They're also weird. So let's take a look at copper. Again, just like argon. Whoops, molybdenum shouldn't be like argon, my bad. Molybdenum should be krypton. Right? Copper, you would say it's going to be 4s2, 3d9. You'd be wrong. It is 4s1, 3d10. And again, this has been shown experimentally time and time again. And it's the same for silver and gold. So know these exceptions. When you have these kind of half-filled orbitals, energetically, they're more stable. And if you think about this 4s orbital and then the accompanying d orbital, this energy gap is very small. So this energy difference is small. And so which one is lower or higher energy gets into a very complicated question. So we'll just say things get complicated. You might hear somewhere that half-filled orbitals are energetically favorable. That's a statement some instructors will use. I'm not a big fan of it, but if you like it, you can use it. That's fine. What I recommend is just remembering these kinds of exceptions. And so if you go to your ptable.com, right, if you go to Chromium, if you don't believe me, you can see right over here, we're on Chromium, 4s1, 3d5, just like I told you, right? And same thing for molybdenum, 5s1, 4d5. When you go down to tungsten, it actually doesn't happen. You see 4s2, 5d4. Weird. Copper, gold, or copper, silver, and gold will do the same kind of similar thing. 6s1, 5d10. So just know those exceptions for transition metals.